Today we're going to dive right into a Stack Overflow, but first we need to get a handle about what's going on in memory. Seems like every book does this a little differently. This is my conglomeration of everything I have on the subject, with our low memory addresses up here at the top and our high memory addresses down here at the bottom. Some sources would have me flip the whiteboard over, but this is how we're going to look at it today. We have our simple visualization of a program in memory. We have text segment, data segment, BSS segment, and heap segment up here at the top. We're going to look at those in future tutorials, but what we're really interested in today is our stack segment down here. So inside of the stack segment, we have a frame for main. Main is what's called when the program starts. So this frame of memory is held between EBP and ESP. EBP is the extended base pointer, and ESP is the extended stack pointer. EBP at the high memory address and ESP at the low memory address. EBP and ESP, those are registers. You can think of registers as places where the CPU keeps information it needs. Another interesting one is EIP, which holds the memory address of the next instruction that the CPU wants to execute. So between ESP and EBP, we have all of the local data for main. But let's say that main wants to call another function while it's executing. We would need to know where we need to start when we get back to main. We don't want to start main over again once function is done executing. So we take note of the next instruction in main that will need to be executed when we return. We push that onto the stack. Return address. And then when main calls the next function, let's call it function. A frame for that function is put on the stack, right here. And then all of the local data for function will be housed here in that frame. And EBP and ESP are no longer interested in main for right now. They're interested in function because that's what we're currently executing. So these will instead be pointing to the low address for function for ESP and the high address for function EBP. And then we'll put our local data here. And so function will execute, and then when function is done executing, we'll find the return address here, and that'll be pushed into EIP, and then we can return to main and execute normally. Now let's look at a simple C program to illustrate what we've just learned. First we have our include functions, which tell us to include other C libraries, in this case string and standard I/O. And we have a function called overflow, which all that does is print out execution hijack to the screen. Then we have another function called function. It has a single parameter, a character string, has a local variable, character buffer with 5 characters. We have this function here, string copy, which takes our parameter and copies it into our local variable buffer. Then we have main, which is what is executed when the program starts. Takes some command line arguments. First thing it does is call function with the first parameter from our command line being passed to function. And when that's done, it prints out executed normally, and that's all it does. Notice that overflowed is never called. We'll look into why that is later. Let's compile the program. I'm going to give it debugging, so that'll make it easier for us to look at in our debugger. And then we see that we have a couple other options here. These turn off protections against buffer overflows, but we want to learn about them, so we're going to turn those off here. Go ahead and do that. And then let's open our program in our debugger. And let's list out our instructions. We see some of them here. Some more. Alright, let's set some breakpoints. Setting a breakpoint will pause the execution of the program so we can look at our memory. The first breakpoint I want is right here, right before function is called in main. So I say break 16, and it will break right before a function is called. Let's also set a couple more. let's set a breakpoint inside a function at line 10, right before string copy is called. And let's set a third one right after string copy is called at the next line, so break 11. Now let's run our program. And knowing what we know about the program and how the buffer wants 5 characters or less, let's run it normally by giving it 5 A's. We hit our first breakpoint, so let's examine our memory. Let's print out 64 words after our ESP. We look here. Let's remember what we saw on the whiteboard. ESP would be here. Then somewhere in here will be our extended base pointer. Let's actually find out where that is. Alright, we see that is at this address, and that would be right here. That would be right here. So between here and here is our frame for main. Everything looks as we would expect. Now let's continue. This will call our function and begin execution. Then we'll hit our second breakpoint right before the string copy is called. Let's look at our memory again. We see that we're at lower memory addresses, which is what we would have expected, as we've put on the frame for our function on top of or below, if we're thinking in terms of memory addresses, our main frame. Now let's remember where main was. And this should be our EBP for main. And then here should be our ESP for main. This should be the return address for main. This should be EBP for our function. And we already know this is ESP. Let's look and see if we're right about EBP. And it's at this address, 58. It is right here as we expected. Let's look at this return address. Since the last thing that was executed was the call to function, we would expect that return address would be the line right after that in main. Let's see if that's true. Let's disassemble main. And here we see our call to function, which was the last thing that was executed. And then we see the next function to be executed is this memory address right here, which is what is in our return address. So everything is as expected. So let's go ahead and continue and execute our string copy, and we hit our third breakpoint. Let's look at our memory one last time. And it looks about the same here, except we see our 5 A's here. Let's go ahead and let it finish. And it executed normally. We see our printout of executed normally, which is what we would expect from main after it finishes. Let's look back at our program visualization in memory. So let's say the function has already been called by main, and so its frame has been put on the stack. And we remember from our code that one of the local variables for function was a 5-character buffer. So 5 bytes will be allocated inside this frame for that space. And when string copy gets executed, we had 5 A's copied into that buffer space. And then that's everything that function does. So execution will return to main. All this will come off the stack, and then our return address from before will be copied into EIP. So then that will be executed by the CPU and will continue on through main. Let's look back at our C program. Remember, what we just did was run it with 5 A's, which we saw here in memory, and everything executed normally. But let's remember how this works. If we look at our function, it uses this function here, string copy, to copy our parameter into this 5-character buffer. Let's see what happens if we run it with lots of A's. We hit our first breakpoint. Let's go ahead and continue. And then we hit our second breakpoint right before the copy. Let's continue again. And we're seeing something strange here as we hit our last breakpoint right before function returns back to main. We're seeing address out of bounds here with some A's. Let's go ahead and continue and let this function return and give the control back to main. And we see we had a segmentation fault. Our program tried to execute this memory address here, and it didn't work out so well. It was overwritten with A's. Let's see why that happened. The first time we ran the program with 5 A's, everything worked nicely because our 5 A's fit nicely inside of our 5-character buffer, seen right here. But if we try and run the program with lots of A's, we can see our problem in the visualization. Every time an A is copied in, it's copied into a higher memory address. So instead of filling up space here in the unallocated space on the stack, what we actually end up doing is copying over the rest of our function frame. So some more A's here going down the stack. And then even our return address. So we end up with 4 A's here. The return address is 4 bytes long. And it could even end up overwriting some of main. So then after the string copy happens, that's the last thing that happens in function. So this will get popped off. And then we'll try and return to main using this return address. So that gets copied into EIP. And since that's been overwritten by 4 A's, the CPU will try and execute 41, 41, 41, 41, which is hexadecimal for 4 A's, but that doesn't work out so well. But if we study this and see exactly how many A's we need in order to reach the return address, instead of just copying in 4 A's, we could return in the memory address here of some instruction somewhere in memory, so we can actually execute code instead of just crashing it. So let's look at that in our debugger. This time, let's try to directly control the return address and execute code rather than just getting a seg fault. First, let's look at our breakpoints. And let's delete the first 2 and just keep the one right after the string copy. Now let's run the program again. But this time, let's make our string with Perl. Going to do 5 A's again, so it will run normally. Let's run this. We hit our breakpoint, our only remaining one right after the string copy. Let's look at our memory. And we see, like before, our 5 A's. Remember, here is our EVP. And this will be our return address. So to directly overwrite this, we can calculate the offset. 16 bytes here, plus 4 and 1. That'll be 21 total. So let's run this again. But this time, let's do 17 A's, dot for concatenation in Perl, and B times 4. Let's run this. Hit our breakpoint. Let's examine our memory. And we see we have A's all the way up through here for our breakpoint, which is overwritten with 4 B's. So what we suspect is that we'll get a seg fault again, but it will be trying to execute the 4 B's. And that's exactly what happens. Let's go back to our program. And remember this function here, overflow, that never gets executed. Let's actually change this program a little bit so that it does execute overflowed. Let's go ahead and compile it and open it in our debugger. And let's disassemble main. And if we look here in our assembly code, we see where overflow is called in the program. And let's take note of this address here. This is the memory address of overflowed, the function. Let's take note of it in Notepad so we can remember this address for later. go ahead and exit out of here. And let's edit this again and take Overflow back out. So now Overflow will once again not be executed. Let's go ahead and recompile it with the change and open in the debugger again. Add our breakpoint at line 11, which is right after the string copy as before. And now let's run this program again. Going to use Perl again. Do 17A's again to get to our return address and concatenate that with our return address. And let's remember what that was. Alright. Just add those hex bytes in. Alright, let's run this. And we hit our breakpoint. Let's look at our memory. And our A's seem to have worked out fine. We seem to have a problem here. Our bytes seem to be backwards. Let's look at why that is. So when we got to our return address, we saw that it was backwards. This is due to Endianness. Anybody read Gulliver's Travels? Remember when he got to Lilliput? They were having a lot of problems there because they couldn't decide which side to crack the egg on. One side said you had to do it on the little end, and the other side said you had to do it on the big end. Well, there's something similar going on in terms of CPU processing. There's the big endian side and the little endian side. The big endian side says that the most significant byte should be copied in first. So in that case, the address would come out normally. But then there's the little endian side, and they say that the least significant digit, the byte here, should be copied in first. It would end up here, and then the next significant being up here, and so on and so forth. So really, little endian, it just comes out backwards. And since we're using an Intel processor for our screencast, it's actually using little endian. So that's why it came out backwards. So if we just flip our digits around here and have our byte 14 first, and then our 84, our 04, and our 08, and it's just flipped around, then everything should come out normally. Okay, taking into account what we know about Endianness, we should be able to fix this by just flipping these bytes around. Now we should have the correct return address. Let's run this. We hit our breakpoint. Let's look at our memory. And this time, it looks exactly like what we want. This is the address for the overflowed function that we want to call. When we continue, exactly what we expected. Execution was hijacked. It means the overflow function was called. We were able to successfully hijack the execution of the program. However, we did receive a seg fault after that. This makes sense if we look here, next address. After the overflowed function finishes, it will return and look for its return address right here. And that's exactly what happened. We'll look at fixing this so the program keeps running in future tutorials. The moral of the story is that the string copy function didn't check to make sure all those A's could fit inside the 5-character buffer before it made the copy. So either we need to stop using that string copy function or check our bounds manually to stop from getting an overflow. So now you've done your first Stack Overflow. Next time we'll look at Immunity Debugger and doing a Stack Overflow in Windows. See you next time, and don't forget to dance when your execution hijack works.
Done.